Hi everyone, I have a great pleasure of hosting at today's seminar Tomasz Kociumaka. Tomek is currently at Bar-Ilan University. Tomek, please start.
Thank you. Thanks for inviting me and thanks for coming to this seminar. In this talk, I'll speak about approximating text-to-pattern Hamming distances, and this is joint work with Timothy Chan from Illinois Urbana-Champaign and Shay, Golan, Tsvi, Kopelowitz, and Porat, which are all from Bar-Ilan University, like myself. And this work has been published at STOC 2020, so it appeared just last month. I'm sure everyone knows what a Hamming distance is, but let me define it formally nevertheless. So Hamming distance of two equal length strings simply counts the number of mismatches between the strings. It is the number of positions when there are different characters and the positions are aligned. And in this example, we have a pair of strings with Hamming distance 4, and the 4 mismatching characters are marked with a not unequal signs. And the main problem which we study in this paper and which I'll speak about in this talk is the problem of text-to-pattern Hamming distances. So in this problem, we are given a text T of length n and a shorter pattern P of length m. And the goal is to compute the Hamming distances between the pattern and all the length m fragments of the text. So in other words, the goal is to output a sequence D, and the ith element of the sequence di is supposed to be the Hamming distance between P and the fragment of T starting at position I and ending just before position I plus m. And here is an example. So the first element of the sequence is the distance between the pattern and the prefix of the text. It's 2 in this case. For the next fragment, the distance is 4. Then it's 2. And in a similar fashion, we can construct the whole sequence di up to the distance between the suffix of the text and the pattern. So that's the text-pattern Hamming distances problem. And it's a very classic problem. Already the first non-trivial algorithm is already from the 70s. It's by Fisher and Patterson, who showed that the Hamming distances can be computed in n log n time multiplied by the alphabet size. And the main idea behind that algorithm is to count the matching occurrences for each character C in the alphabet, so matches between occurrences of C in the pattern and occurrences of C in the text. And such matching occurrences can be counted for each shift, for each offset, using a single convolution, which is implemented via the fast Fourier transform. And that's why the running time of the algorithm is n times sigma times log n. And this log n can be improved to log m, but in this talk, I will generally assume that the ratio between the length of the pattern and the text is constant, so that we will not take too much care about improving n to m in the running times. So the first improvement for this algorithm was from 1980s by Abrahamson and Kosaraju, who independently observed that characters which are infrequent in the pattern can be handled much more efficiently if we count the matching occurrences more naively. So instead of using FFT, we simply consider each occurrence in the pattern and each occurrence in the text and increment the counter of matching occurrences at the position when they get aligned. And setting appropriate threshold between frequent and infrequent characters, this leads to the running time of n square root n log n. And this is still the state of the art of the problem. More recently, there's been a lower bound saying that there is no faster combinatorial algorithm, which essentially means that you can reduce the problem of Boolean matrix multiplication to computing the text-to-pattern Hamming distances. And this means that if we want to improve the running time significantly beyond n to 1.5 by any polynomial factor, then we will need to use some algebraic techniques also yielding faster Boolean matrix multiplication. So in particular, we might need using a fast matrix multiplication algorithm. However, we still don't have any such algorithm, even using fast matrix multiplication. And obtaining such an algorithm would be a major breakthrough. So it's, I believe, the biggest open problem in the area. And even the annoying square root log n factor is still there, and we have no idea how to get rid of it. So given that this complexity is not nearly linear, it's quite large in some settings, much research is devoted to the approximate version of the problem, in which we relax the conditions on the output. So the input also contains an error parameter epsilon, which is a real number, a positive real number, which we assume to be quite small. And on the output, instead of the exact Hamming distances, we are allowed to give 1 plus minus epsilon multiplicative approximation. In other words, we produce the sequence d-tiled so that of approximate Hamming distances, so that the approximate distance is at least 1 minus epsilon, the exact distance, and at most 1 plus epsilon, the exact distance. And that's the main problem I will be talking about in this presentation. And the first algorithm for this problem is by Karloff. It's an IPL paper from 1993, and he showed that these approximate Hamming distances can be computed in nearly linear time for constant epsilons. Namely, the running time is epsilon to the minus 2 n log squared n. This is a randomized algorithm, and it uses random projections to the binary alphabet and then computes the Hamming distance exactly in the projected strings. And based on these values for multiple projections, it estimates the Hamming distance between the original pattern and the original text fragments. And as this algorithm and most other algorithms in this talk are randomized, the assumption we are going to work with is that the answers should be correct with high probability. So we are working with Monte Carlo randomized algorithms, and for each output d tilde I needs to satisfy the conditions shown on the previous slide with probability at least n minus inverse polynomial, where the exponent in the polynomial is arbitrarily large constant given on the input. So that's Karloff's algorithm, the randomized one. Karloff also had a deterministic counterpart, which is slightly slower by an extra log n factor. But all the subsequent algorithms are randomized again, and we don't know of any deterministic versions. So the first of those is Index from 1998, and he considered the decision version of the problem. So then now the output is relaxed, so that instead of computing the approximate Hamming distance, we just need to check whether the Hamming distance is approximately smaller than k or approximately larger than k for some threshold k. And this approximately means that for distances which are roughly k, between 1 minus epsilon k and 1 plus epsilon k, the answer can be arbitrary. And what he managed to do is he managed to shave off 1 log factor at the cost of an epsilon inverse factor. And the main technique behind this is bit tricks which are needed to compute convolutions modulo 2. So convolutions modulo 2 can be computed in linear time. FFT in that settings works in linear time, and rather than n log n time when we need to deal with larger integers. However, when we consider the original problem of computing the Hamming distance, not just the decision version, then the running time is worse than Karloff's. An improvement came only much more recently with a series of 2 papers by Kopelowitz and Porat, who managed to improve the epsilon dependency from inverse quadratic to inverse linear. In the first paper, they had a much larger polylog factor, but in 2018, they improved it to log squared n, which matches that in the Karloff's algorithm. And the main techniques are quite similar than Karloff's, namely they also use random projections and compute the exact Hamming distance as after the projections, but instead of binary alphabet, they use alphabet of size inverse linear in epsilon.
And this is for the original approximation?
Yes, yes.
Okay.
Yes, and yes, by the way, feel free to interrupt me, yes, this one, because this is like a 45-minute talk, so it's much better if you ask questions during the talk than later. Okay, so that's the state of the art, and we can see that when we stick to the original version of the problem, we have this log squared n factor in all three algorithms. And the main question behind this research is whether this log squared n factor is necessary. So can we beat this n log squared n running time? Maybe even for arbitrarily small constant epsilon, so maybe we allow for larger dependency on epsilon than inverse linear or even inverse quadratic. And since all those algorithms are using convolutions and fast Fourier transform, an auxiliary question is whether we really need to perform those convolutions and to actually perform so many of them. So in all those algorithms, the number of convolutions is at least logarithmic, and this is the bottleneck. And the answer to both questions is yes, as we show in the paper. That's the main result. Namely, we managed to obtain truly linear algorithm when it comes to dependency on n, and our dependency of epsilon on epsilon is inverse quadratic. So the running time is epsilon to the minus 2 times n. So this is strictly better than Karloff, but the dependency on epsilon is worse than in the simple algorithm by Kopelowitz and Porat. And on the way to achieving this result, we also show that we can do this actually without any convolutions. So we are not using FFT whatsoever. However, this algorithm is quite technical, so in this talk I will just describe a more modest improvement upon the n log squared n barrier, namely an algorithm whose running time is epsilon to the minus 2.5 n log to 1.5 n. So we shave off square root log n factor and increase the dependency on epsilon to even worse than in Karloff's algorithm. But before that, let me quickly recall the techniques behind previous algorithms. Two such techniques. The first one is alphabet projection, which is common to Karloff and Kopelowitz and Porat. And I will explain it based on the latter algorithms. It's a SOSA paper, so you might expect a very simple algorithm. And indeed, it will fit on this slide. So as I said, the first step is to draw a uniformly random projection from the input alphabet to a smaller alphabet of size 2 epsilon to the minus 1. And then we compute the exact Hamming distances after the projection. So we project both the pattern and the text using this projection of alphabet. And for this exact version, we use simply the algorithm of Fisher and Patterson. And now let's see how the exact Hamming distances after projection are related to the Hamming distance before the projection. So each pair of matching characters stays a pair of matching characters because the projection is a function. And also a pair of mismatching characters is very likely to stay a pair of mismatching characters. Collision probability is epsilon half. So probability 1 minus that, a mismatch remains a mismatch. And now we can use Markov's inequality to show that the distances after the projection, which will be our approximate distances, are with probability at least half larger than the original Hamming distance. And this holds for every single offset I. So it's not for every single offset with probability at least half. This is a good approximation. And this is also we are doing a one-sided error because matches remain matches, so we can only underestimate the Hamming distance. However, this probability is valid only for every single position, not for the union, not for all the positions at the same time. So for every particular instant, we expect that half of the output is not going to be correct. So this is far from satisfactory. And that's why we repeat the whole process log n times. And this way we boost the probability to error probability becomes inverse polynomial. Success probability is high. And we simply take the maximum of the estimates because of the one-sided error property. And this gives us...
I'm a little bit confused here.
Yes?
Isn't that the other way around? That if you have a mismatch somewhere, it will be if you discover a mismatch after a projection, it surely gives you a mismatch in the original alphabet, right?
Yes. So that's I was in the direction of those implications is a mismatch in the original string remains a mismatch. Not necessarily remains a mismatch in the projection. If you look,
yeah, that's true,
at it from the perspective of the other string, then a match might become a mismatch if you go from the projected string to the original strings. So it depends on from which pair of strings to which you go.
So what do you mean by each mismatch remains a mismatch with probability something?
So each mismatch in the original between characters in the original strings remains a mismatch between the corresponding characters of the projected strings.
That makes sense.
With probability at least 1 minus epsilon 2. Okay, thank you. I hope it made it clear for all of us. And yes, and when we are only this way, we only underestimate the Hamming distance, and we are not underestimate by too much. So yes, we repeat, and after log n repetitions, we get good bounds with high probability. But well, here this log n seems unavoidable. This log n repetitions, and also we are really using Fisher and Patterson's algorithms, which has this FFT inside. So the 2 log n factors look really hard to improve upon using this approach. So let's see another technique, which is to use sampling in order to estimate the Hamming distances. And in order to do so, we need to focus on distances in a certain reasonably small range. So I will define a relaxed version of the problem when we have an additional threshold k, just like in the decision version. But now we will need to approximate the distances which are between k and 2k. And for the distances smaller than k, we will be able to say that they are smaller than k, but without obtaining a good approximation. And similarly, for distances larger than 2k, we allow just saying that these distances are larger than 2k, and this is formalized by producing estimates which are significantly smaller than k and or significantly larger than 2k in order to allow smoothly and seamlessly dealing with these cases where the actual distance is not within the range we expect it to be. So we either return a good approximation or say the distance is small or the distance is large. And another caveat is that this version only requires large constant probability for each particular index. So that's the same property as we had in Kopelowitz Porat algorithm, just for a single projection or for a constant number of projections if we want to have the probability to be larger than half, but still constant. And now the reduction to the original problem is relatively simple. First of all, we need to repeat the process log n times to boost the success probability to make sure that the answers are correct with high probability and we don't expect any errors across all the offsets or all the fragments we consider. And then, since every particular instance of this algorithm needs this threshold k, in order to approximate distances in the whole range between 1 and m, we need logarithmically many levels, with each level having k, which is a power of 2 between 1 and log m. So that's essentially 2 log n factors, which are on top of any running time for the relaxed version of the problem. Okay, so now we are looking for Hamming distance between k and 2k, more or less. And that can be estimated by sampling. And one way of doing so is to, in order to compute the Hamming distance, estimate the Hamming distance between n and s prime, we can sample positions independently with the same rate of 1 over k. So we sample those positions, and we look at the underlying characters, and we check if there is any mismatch among the positions we considered. In this case, there is one. And the probability that you will not see any mismatch can be computed exactly. This is this value, 1 minus 1 over k to the power of Hamming distance. That's because for each mismatch, the probability that we miss this mismatch is 1 minus 1 over k, and the events are independent because our sample takes each position to the sample independently with the same probability, 1 over k. And now it turns out that if you repeat this process epsilon to the minus 2 times, then the count of the number of iterations with a mismatch detected, as opposed to those iterations with no mismatch detected, can be used to approximate the Hamming distance. And that's relatively easy using Chebyshev's inequality, but I will not have time in order to get deeper into the calculations. So that's for a single pair of strings, but our problem is to consider all the fragments of T and the pattern P. So the naive way to apply this sampling approach is to process each of those offsets, each of the fragment independently, but that's quite slow. We have n of those offsets. For each of them, we have epsilon to the minus 2 repetitions, and then the sample size is in expectation m over k. So in total, we have this n epsilon to the minus 2 m over k for the relaxed problem. And for the original problem, if we boost the probability and consider all the thresholds k, then we get something which is even worse than the naive algorithm, just computing everything position by position. So not very interesting. But sampling has already been used in combination with more tools, including fingerprints. So Karp-Rabin fingerprints are the most standard way of hashing strings into small integers. They are also known as polynomial hashes in some communities. And such a fingerprint interprets strings as strings, not others, an arbitrary alphabet, but the alphabet is assumed to be a finite field with characteristic Q. And these fingerprints interpret the string as a polynomial. So the ith character of the string is interpreted as the ith coefficient of the polynomial. And the value of the fingerprint is simply the value of the polynomial at a random point in modulo Q. And this is a function. So whenever we have the same matching strings, we have matching fingerprints. But also, if Q is large enough, if the strings are different and of the same length, then the fingerprints are going to be different with high probability. And so that means that this is a good hash function. But it also has further nice properties. Namely, it's linear, just a linear mapping from strings to integers. And it's rolling, meaning that we can cheaply append a character to both endpoints, and we can cheaply drop the leading or trailing character. So if you have some extra infrastructure, this can be done in constant number of arithmetic operations modulo Q and in constant time, consequently. And this way we can implement the idea of sampling significantly faster. So let me recall that we draw a sample of positions between 0 and m minus 1, and we do it with rate k. Then we consider the pattern in the text, starting from the leftmost fragment of the text of length m. We consider the sampled positions in the pattern, and we compare them with the aligned positions in the text. We compute the fingerprints of the strings obtained. And now we compute the fingerprints from the strings obtained by those sampled positions. So we ignore all the positions which are not sampled, and we stitch together all the sampled positions, and we compute the fingerprints both in the text and in the pattern. And the fingerprint in the pattern is going to be the same for all the alignments, but the fingerprint in the text needs to be different. So when we go to the next shift, it will be different. And still, because these are fingerprints, we have the same property that we got by just comparing the individual positions. So when the fingerprints are equal, then with high probability, the pattern matches the fragment of the text on all the sampled positions. And if the fingerprints are different, then we are sure that there is a mismatch among those positions. So the test is pretty much the same, and we can ignore the events happening with inverse polynomial probability. And now the shifting can be implemented more efficiently. Namely, when we can observe that the shifting can be implemented again using FFT, because we are always computing a cross convolution with the same, essentially the same polynomial in this case, which is x to the I for the ith sampled character, for the ith smallest element of the sample. And this means that we can compute all the fingerprints for all the offsets in n log n time. So that means that for a single R, for a single sample R, our running time is n log n. We have to repeat this epsilon to the minus 2 times for the relaxed version of the problem, and then we get an extra log squared n factor for the original version. And actually, this approach was used by Indik in his algorithm, but he managed to shave off a log factor at the cost of epsilon to the minus 1 factor, because on top of that, he used, again, alphabet projections to binary strings, and the fact that he used binary strings allowed him to use convolution over Z2 instead of over integers or ZQ. But that's not the path we are going to follow, so we are omitting the details of Indik's algorithm, and let me proceed to our ideas. So our main contribution is that we make sampling more structured. And the structure is as follows. So we have an auxiliary parameter P, and this P is a random prime number of size roughly k, epsilon to the minus 1 k log n. And instead of sampling among the positions between 0 to m minus 1, we just sample from 0 to p minus 1. And then we repeat this periodically every p characters. So our actual sample contains a position j if and only if its remainder modulo p belongs to the sample b. In other words, the event that we include a position in the sample are independent if the positions are different modulo p, and they are completely fully dependent if they are the same modulo p. Nevertheless, it turns out that this is still sufficiently independent to estimate Hamming distances with good probability. Namely, what we actually do is we replace the true Hamming distances by the number of different remainders modulo p that the mismatches have, and given that p is large enough and random, we can show that this doesn't differ too much from the original Hamming distance. The thing we lose is epsilon fraction of the mismatches, which is fine. And now the setting is still the same. We look at the sampled positions, we stitch them into strings, and compute the fingerprints. And now the new thing that happens is that when we shift by p characters, rather than by just one character, we can recompute the fingerprint on the text quite efficiently. Namely, we can use the rolling property of Karp-Rabin fingerprints and observe that the only thing we need to do is to drop some of the leading characters and append some of the trailing characters. And the number of characters we drop and append is exactly the size of b. So with these particular values is epsilon to the minus 1 log n. And this way we can further shift by multiples of p. So what's the running time? So for the first p shifts, for the first p offset, we need to compute the fingerprints using the old method. So by just looking at every single sampled character in m over k time in expectation. But for the remaining ones, we can update the fingerprint from p positions before, and that costs epsilon to the minus 1 log n time per shift. And in total, we get epsilon to the minus 1 n log n. That's again for fixed sample R. And we need to take into account epsilon to the minus 2 samples and an extra log squared factor to achieve something for the original problem. So what we get is epsilon to the minus 3 n log cubed n, which is not particularly good running time. It's worse than Karlov, but at least we are not using FFT. So we have managed to answer the second auxiliary question, but not the first main question. And to answer the first main question, I'll also need to show a little bit different way of implementing the idea of sampling with fingerprints, of our structured sampling with fingerprints. And now, instead of computing many samples and many shifts in the text, we will do so in the pattern as well. So we construct the sample in the same way. And for the first shift, everything works like previously. But now we are going to read only the characters of the text which are whose remainders modulo p are in the sample B. So we will never touch the other characters. We will never read those characters. And now, in order to advance from this offset 0 to the next offset 1, we will consider a different shift in the pattern. So now in the text, we just have a sliding window. And this is a sliding window over the sampled positions. So in every when we shift by a single character to the next offset, maybe something enters the sliding window, some sampled positions enter the sliding window, and some sampled positions leave the sliding window, and maybe not. But anyway, this is just one position, so it can be handled quickly. But for the pattern, we need to take a completely different sketch. Like here, the sampled position in the pattern changed completely, but in the text, we just need to do something much simpler. Nevertheless, since the pattern is fixed, but it's in the text when we need to consider multiple fragments, multiple offsets, the number of fingerprints we need to compute for the pattern is still just p. After p steps, we go back to the original fingerprint for offset number 0. So the running time is now p times m over k again, and this is for computing this time the fingerprints in the pattern. But in the text, we managed to handle each particular offsets in constant time now for a fixed r. And that's because just one thing enters the sliding window and one thing leaves the sliding window at most one. It's actually 1 over k in expectation, but we still need to compare the fingerprints, so the linear dependency on n is still needs to be there. And again, by multiplying by epsilon to the -2 and log squared n, we get the running time for the original problem, which is still not particularly satisfactory. Namely, if m is proportional to n, we didn't improve, and we didn't get any improvement compared to the previous algorithm. The only thing is that we replaced n by m in the first factor, and the second factor is just the running time of Karlov's algorithm, so it's not particularly impressive either. But the two approaches can be combined and carefully balanced. And for this, we compute fingerprints both for the shifts of the pattern and maintain many sliding windows over the text. So for the pattern, we compute the fingerprints of z shifts. These are shifts from 0 to z-1, where z is some threshold parameter, which we're going to optimize when computing the time complexity. And for the pattern, we maintain fingerprints for p over z shifts, modulo p. And these are shifts which are multiples of z. And now for every offset I, it turns out that there is a aligned shift among those considered in the pattern and among those considered in the text. And to obtain the actual indices, you just need to divide I modulo p by z with remainder. And then this gives the actual indices of the shifts that need to be considered among those for the pattern and among those for the text. The running time, calculating the running time is a little bit more challenging, so we need to do it in 3 steps more slowly. So first of all, we have computing the fingerprints for shifts in the pattern. We have z of them, and for each of them, we just naively consider each sampled position, m over k of them in expectation. So that's the first term. Then we have shifts in the text. So now here you have sliding window, and the sliding window goes over the sampled positions in the text. So the fingerprint in the text changes only if something enters or leaves the sliding window. And the number of sampled characters in the text for a particular shift is n over k in expectation. And we consider p over z of those shifts. So that's so P over Z times N over K is the term coming from maintaining the fingerprints for the text. And finally, we have linear time, which is necessary to compare the fingerprints, to compare the appropriate fingerprints among those for the pattern and among those which are currently maintained for the text. So the overall running time is this if you optimize for Z. So it's linear in N from the first term, and the first two terms meet at square root nm log n over epsilon k, which is kind of not so intuitive running time, but you can think of nm as upper bounded by n. So this is roughly n times log n to the 0.5, and there is also some small dependency on epsilon and inverse square root dependency on k. However, we still for fixed r, and we need to multiply by epsilon to the -2 for the relaxed version of the problem, and we need to multiply by this extra log squared n for the original problem. This is what happens with the first term. As far as the second term is concerned, we multiply by 1 log factor to boost the error probability, but by considering multiple levels, since we have a dependency on k in the running time, we get a geometric progression which is well dominated by the largest term, which in this case is for constant k. So the running time is, as far as the second term is concerned, epsilon to the -2.5 square root nm log to 1.5 n. So this is even slightly better than I promised because we have m instead of n. But the first term is still like in Karloff's algorithm. And even after all this hard work, we are not better than Karloff, which is quite disappointing. But now our bottleneck is very simple. Namely, the only thing that dominates the running time and gives rise to the first term is that we had to compare all those fingerprints for every offset, for every iteration due to boosting probability, and for every level k. And once you look into this, maybe you can hope for improving the epsilon dependency in this term, but if we keep our definition of the relaxed problem, there is not really hope we can improve the log squared n factor. That's because the relaxed problem needs at least linear time to produce the output, and then our reduction multiplies this n by log squared n. So we need to slightly change the definition of the relaxed problem, and we add some kind of adaptivity to this problem. Namely, we introduce a set of positions, set of offsets Q that is going to be revealed online in the left to right fashion. And now we relax the problem further so that we require outputting anything only for the positions in the set Q. So you can think of Q as kind of queries. So whenever we get to time I, to processing offset I, the user can decide if he's really interested in this offset or if we should just go to the next offset. And the conditions are exactly the same as in the original version of the standard relaxed version of the problem. So this adaptivity allows improving the running time because our sole bottleneck was just for outputting and comparing the fingerprints and then estimating the Hamming distance based on the fingerprints. And since we need to do that only for the queried position, this linear term in the running time becomes linear not in n, but in the number of queries Q. And this gives us some hope for beating Karloff's running time for the whole original problem of approximate text-to-pattern Hamming distances. And that's exactly what we do. Namely, we have the same reduction, essentially. So we still have logarithmically many levels k, and each level has log n instances to boost error probability. So the second term in the running time, which is this one, is still the same, but the improvement happens in the first term. Namely, now we can use the fact that our approximate values say not only that something is within the range between k and 2k, but also distinguish between distances much smaller and much larger than that. And we can use this using binary search. So for every offset I, we just binary search the appropriate level that should be responsible for the offset. So the level that essentially handles distances for which our di is between k and 2k for that particular k. And this means that the number of queries is still epsilon to the minus 2 per instance. So the number of fingerprint comparisons is still epsilon to the minus 2 per instance. And each level still has log n instances because we need high probability of success. But now for every particular offset, we query only log m levels instead of log m levels. And that's because we are doing binary search rather than looking at all the levels sequentially. And combining the two running times, we get finally what I promised, which is epsilon to the minus 2.5 and log to 1.5 m. And that's the these are the main ideas, but with these techniques, you can go slightly further. So as I promised, you can get all the way to linear dependency on n. This requires a few steps. I'll just very briefly overview the techniques behind those. So first of all, instead of Karp-Rabin fingerprints, we actually use binary fingerprints. So we compose Karp-Rabin fingerprints with some random mapping to 0 or 1. And then we use bit packing tricks to make sure that we can compare multiple fingerprints in constant time. And that reduces the second term in the running time. In order to reduce the first term, we observed that the bottleneck there was for very small k. And there are efficient algorithms computing the Hamming distances exactly if we only care about small distances. And this lets us completely remove the first term. It gets dominated by the second one. So this is almost there. We have just this annoying log m factor, and for this we use very dirty bit packing tricks like matrix transverses and so on, and that we only describe in the full version archive. It's not even there in the Fox extended abstract of some 15 pages or so. So this is how we get this linear running time with inverse square dependency on epsilon. But our techniques lead to further results as well. First of all, we can improve something in exact version of the problem too. So then there is an algorithm by Przemek and Paweł Gawrychowski who compute the distances up to k efficiently. And in this algorithm, we managed to shave most of the log factors. The only log factor left is also already there in the approach by Abrahamson and Kosaraju. So essentially, for any further improvements for this version with k would probably yield an improvement for the version without k. Then, interestingly, we managed to remove the epsilon dependency whatsoever when epsilon is large enough compared to m. The condition is quite horrible. Namely, we require that the pattern is of size at least epsilon to the minus 28 to achieve nearly linear running time. But the most interesting thing behind this is that we use fast matrix multiplication here. So maybe there is this will open some paths of using this fast matrix multiplication for text-to-pattern Hamming distances. And in particular, here we use the fact that very thin matrices can be multiplied in time nearly linear in the output size. And the ratio between the dimensions of those matrices is why we get such a constant 28. We also observe that our main algorithm essentially doesn't need to read the whole pattern and the whole text, assuming that we only care for sufficiently large distances, and this leads to sublinear time algorithms for large k and constant epsilon. And there we also need to use techniques such as near neighbor search in order to locate the occurrences. And a particular consequence of the sublinear time algorithm is a property tester, which simply distinguishes between instances where the pattern has an exact occurrence and instances where the pattern doesn't even have an occurrence with hamming distance delta times m. So this is an additive error of delta times m, essentially, and only to the exact case. But this was an open problem in some of the previous work, so in particular, we managed to answer this open problem. And finally, we gave improved algorithms for streaming, improved streaming algorithms for the approximate text-to-pattern hamming distances problem. So we give first algorithm, which is efficient when we only care about distances up to k. And the space complexity is epsilon to the minus 2 square root k. And where k is large, we also managed to improve some epsilon dependency in the space complexity. And the running time is also quite good. It's epsilon to the minus 3 multiplied by some log factors, which are hidden here using the old tiled notation. And in the last minute, let me just conclude with some open problems. So repeating one of the first slides, the main open problem is in the area is to improve the running time for the exact version of the problem. Even shaving off this annoying square root log n factor would be a big result. Then for the approximate version, we now have two solutions which are incomparable. Our new algorithm has linear dependency in n, but inverse quadratic in epsilon, while Kopelowitz and Porat from SOSA 2018 have inverse linear dependency on epsilon at the cost of 2 extra log n factors. So any trade-off or something that subsumes the algorithm would be welcome. Secondly, our algorithm using matrix multiplication shows that the dependency on epsilon is quite strange. So if epsilon is large enough, we can get rid of the dependency whatsoever. But if epsilon is small, then we have this inverse linear dependency, and it's not clear if this is necessary. So this is something which should be studied further. And finally, our approach is inherently randomized. And when it comes to deterministic algorithms, we still only have Karloff's, which has inverse quadratic dependency on n and a log cube n factor. And that's it for the talk. Thank you very much for listening, and I'll be happy to answer some further questions.
Tomek, I have a simple question.
Yes.
If omega is equal to 2, then what is the threshold for the large epsilon?
Yes. Yes, then what? What's the question?
What is the threshold then?
It's something like 10. We haven't really optimized it, but it's something like 10 at the moment. So actually what the actual threshold we are working on is this constant, which is denoted by alpha sometimes, which is the ratio between so for matrices which are n times n to the alpha, these are the matrices that we can multiply in quadratic time, n squared. And the running time, so omega being 2 is the same of alpha being 1, sorry. But our dependency is something like 4 divided by alpha plus 10. But we haven't really optimized it. And we did check what happens if alpha is equal to 1. And we didn't manage to get anything better than quadratic dependency on epsilon when epsilon is large.
Okay, so it doesn't change anything qualitatively, only quantitatively.
Yes, so only the thresholds move a little bit, but we didn't really get deep into that. So also the version we published is not optimized in terms of this dependency, and we have some ideas how to improve this dependency, but still these improvements wouldn't yield such a qualitative results that you might expect.
And what kind of matrix products do you use there?
It's just ordinary product of Boolean matrices.
Okay.
I mean, Boolean, yes, Boolean. So that's actually, we compare those fingerprints, but the fingerprints are mapped into bits, and then counting how many fingerprints, in how many instances the fingerprints were the same and how many are different is something like the inner product. And that's how we reduce to the matrix multiplication very, very briefly. But that's just Boolean matrix multiplication.
Tomek, could you repeat the definition of your property tester again?
The property tester must return yes if there is an exact occurrence with Hamming distance 0, and it must output no if for every fragment the distance is larger than delta times m. And regarding this property tester, is also a nice problem whether you can improve this n to the 2/3 dependency. I would hope that something like square root m should be possible without too much new techniques.
And can you do the same for the Hamming distance threshold? I don't know how to define it. Like, yes, if you have an occurrence with Hamming distance smaller than k, no, if all the occurrences are very far from that.
So that's essentially what our sublinear time algorithm does.
Okay.
But it doesn't work when k is small. Like, it's not sublinear again. It's not sublinear anymore if k is small.
Any other questions?
And for the property tester, this is the query complexity, right?
This is the running time.
And like normally for property testers, you rather measure everything in the query complexity. Well,
yeah, but it's not, the query complexity is not better. I mean, it has less log factors, but it's the same.
Okay.
Okay, thanks, Tomek, for the talk.
Thank you very much for inviting me.
I will stop the recording now.
Okay, thanks.